Dear students, today we will see the concept of virtual memory. As name itself suggests, virtual means it is an illusion. It is not in existence, but with the kind of implementation, the techniques used, we can have virtual memory, which will help us to do three basic things which are better than what we are doing through the normal memory management techniques. One is we can write programs which are bigger than the main memory size, or we can call it as physical memory size, and we can speed up the process and we can use the CPU in a better way. So let us understand that one with this particular diagram. Here we can see a virtual memory, components of the system which has the virtual memory. So here you can see virtual memory, then I have a memory map, then I have a physical memory, then my secondary memory where major of my information is stored here. And by looking at this, we can find that virtual memory looks bigger than the physical memory or the main memory, and even the secondary storage. So this is what I was talking, creating an illusion for the system or for the user to make use of this system in a better way. So what we have in virtual memory, we have pages. Pages are nothing but as blocks of memories, which contains definitely the address of the memory where we have the information which we have to be using for the execution purpose. So here I have page 0 to page V, which is virtual memory. Then I have a memory map. So this will help me to locate this virtual address into physical address. Okay, I repeat again, memory mapping will help me to map these two or coordinate these two to get the information which my CPU or a user wants. And as we all know, the working of physical memory, which will provide all required information to the CPU for the execution purpose. And if something is not there, then we have to bring from the secondary memory where my all project or all processes are stored. I hope the concept is clear here. We are creating an illusion which will increase the working or efficiency of the CPU or the memory, as well as the increase the speed of the operations. Students, we have just now seen the virtual memory. Then how to implement it? There is one way, is called as demand paging. As name suggests, what is demand paging? All the processes from the main memory will not be loaded into the virtual memory, or what you call as from the secondary memory to the main memory, or vice versa, or what you call as from main memory to the CPU. What will happen is process has so many instructions which are not used at the same time, at least for the same time. So we will be using, say for example, a project has 100 instructions. At a time we might be using 1 or 2 or 3 or 5, whatever it is. So in demand paging, what will happen is we will bring in only those pages which are in use right now. This is what we call it as demand paging. Whenever a page or information is required from the main memory, will be brought in to the CPU and work will be done, and it will be sent again back to the secondary memory if required, or and so forth. Okay, that's what is here. The basic idea behind demand paging is that when a process is swapped in, its pages are not swapped in all at once, rather they are swapped in only when the process needs them. This is called as lazy swapper. So why lazy swapper? Because whole process is not swapped in, only part of it, and other things will be swapped in whenever it is required. So we should be knowing the meaning of these three terms when we are addressing demand paging. So one is swapped in. We can see here there is a main memory, okay, and there is a secondary memory. What will happen here is swapped in means information from secondary memory will be brought into the main memory for the execution purpose. That means the information which has been asked by my CPU will be brought in from secondary memory to the main memory, and from here it will be accessed in the process system. This process is called as swapped in. Then what is swapped out? See, what will happen is when we swap in some processes from the secondary memory to the main memory and we don't have space, then we need to swap out the processes which are not executing right now, so that my CPU will be kept busy. And that is what we call it as, when we take a program or a process from main memory to back to the secondary memory, is called as swapping out. I repeat, swapping in is bringing the process or program from secondary memory to the main memory. Swapping out is taking out a program, especially if this is a process or a program which is not in use, and sending it back to the what we call as secondary memory, is called as swap out. Now there is something called as page fault. What is page fault? It is nothing but a CPU demands for a particular information or a page, and it search in a table, page table, whatever it is. Then what will happen is that is not available in the main memory, and what will happen then, something called as page fault will happen, and that page has to be brought in from secondary memory to the main memory, then to the CPU. What my page fault is, a CPU has been asking some information or a page which is not there in memory. That situation is called as page fault. Hope all of you understood the meaning of their three basic words in demand paging. One is swapping in, swapping out, and page fault. So what happens here is, let us see how exactly the page fault will be known by the particular system or a particular what you call as CPU. See, here I have a logical memory generated by the CPU. We all know that always CPU generates a logical address. There is a page table required to map between physical memory and this logical memory. Then from there is a secondary memory if required. So here you can see there are 7 pages. All those pages are here: A, B, C, D, F, G, H, T, F. And what has happened is already a frame. Page table contains a frame always. Okay, 2 bits here. One is frame. So this is for the address where A is loaded. Then next, what is this 2, 6? That is C has been added. Then and so on and so forth. So here we can see important part is not this. This is second column. Here we can see something called as V and I. Whenever there is a page or information available in a main memory, then it always says valid bit. V stands for valid bit. And just now I said there is a page fault. How will it come to know? When we say that in page table I means it is called as invalid bit. That means that information is not in the physical memory. That has to be addressed by the operating system itself. Even we can't get it from secondary memory directly. So I hope it is clear. V stands for valid bit. Valid bit means particular information is there in the what we call as main memory. You can say 4, A has 6, C has, and F 9 has. Others are not brought in, they are here. So I stands for invalid bit. I think now it is clear that how we will come to know whether the particular page is there in the or information is there in the main memory or not. Okay, now if a page fault occurs, what has to be done? Page fault is nothing but required information is not there in the main memory. It has to be brought from the what we call as secondary memory. See, here there is something called as load M. Okay, if load M, that is whatever information called as whatever is there in M has to be loaded to the CPU. There are 3 things which usually happens. One is, if that load M is there in the main memory, it is given. If it is not there, then the next thing it is been checked that the load M itself is a valid address or not. What will happen is, sometimes by looking at PCB this can be done. Okay, this will be done by looking at PCB. It looks into PCB whether that particular instruction or information accessed through address space or through address is valid or not. If it is not valid address space, then it will be aborted, the process will be aborted. If it is valid but not in main memory, then the page fault will occur and things will start happening. So that we will see how page fault is handled. Okay, so when a particular process or information is required is not there, then there are three things. If it is there, it will be given to the CPU. If it is not, checked for two things. One is whether that is a valid one. If it is valid and it is not in main memory, then OS will take care that that information will be given to the CPU. If it is invalid address, then it will abort the whole process. So let us concentrate on here. Okay, load M is a information or address which we want to access. The first step what will happen is reference. I said page table. Page table has frames. Each frame has 2 bits. One, as I said, here it is, and here you can see I means it's a that information is not available. V means available, I means not available. Then a reference will be done. If it is not, then it goes to a second step and it informs the operating system that this particular information is not available. What operating system does is, it page is on backing store, because backing store is nothing but my what you call as the secondary storage. Third step is, it sends maps that one to the or picks from the secondary storage that particular page which has been requested by the CPU. And in fourth step, it is sent that free frame, that is the frame which is the page or a frame as you move which is there in secondary memory is placed in the physical memory. That information is brought in here. So bring in missing page. Okay, now what will happen is, once it has been brought into the physical memory, the fifth step is reset the page table. Reset means this I has to be converted into V, and here I should have FF stands for frame. Then what will happen is, again at the sixth step, restart instruction, and the page is available, the process continues. I hope you understood how page handling happens. It happens in total 6 steps. Reference, a trap, if it is not there, page will be, information will be sent by the OS to the system, secondary storage, and information is given main memory, then from to the page table, from to the CPU. I hope you understand how page fault has been addressed. Hope you understood how we implement an virtual memory by using demand paging and steps in ordering in case of page fault. Thank you very much for watching.